we talked about basics of conduction, metals and insulators, semiconductors. So, let me recap what I did in the previous lecture. So, first thing is, for an isolated atom, the possible energies of quantum states are discrete. So, that is one thing, that if you have an atom, the possible energies that electrons can have, they are discrete like this. So, you have this 1s, 2s, 2p, 2s and so on. So, these are different energy levels, and in these you have quantum states, and each quantum state can have only one electron. The second part is, for a gas or vapor of that material, the same energies are available. For one atom you have certain energy levels, and if you have a gas of that particular material where so many atoms are there, the energy levels remain the same. The electrons can occupy only those energy levels, and so this diagram remains the same. Now, the electrons fill the orbital from lowest energy states from here onwards like this. First the electrons will fill this one, then it will fill this one and so on, one per quantum state, Pauli exclusion principle. The last non-empty level may be completely or partially filled. Then we talked about making of solids. When atoms come closer and make solid, then all this energy levels they get changed. So, as the atoms are brought closer to form the solid crystalline state, these outer electrons also start interacting through bonding. You know, the electrons bond the atoms, neighboring atoms. So, those interactions will change the energy levels, and therefore, the energies are split in almost continuous energy bands. So, what was the discrete energy levels now becomes energy bands. So, the energies are split, it is no more a sharp energy level. You have some quantum states go up, some quantum states go down, and so it becomes a band. Then the lower energy levels like 1s, 2s, they are populated by the inner electrons, and the inner electrons they are not much affected because of this bonding and interactions, they do not take part in bonding. So, those energy levels are still sharp, quite sharp, but then the outer ones they spread more, the outer ones they spread much more and the bands are wide. Then the highest completely filled energy band, is called valence band. This is important now. And the next higher band, which is not completely filled, it may be completely empty or it may be partially filled. So, that next higher band is called conduction band. So, these things we talked. Now, what happens in good conductors? In good conductors, the conduction band is partially filled, like here. The conduction band is the red one is denoting filled and the blue one is denoting empty. So, the valence band is completely filled and the conduction band is partially filled, only this much is filled and this is empty. So, in conductors, good conductors, the conduction band is partially filled. There are enough electrons in the conduction band and enough empty states in the conduction band even at very low temperatures. So, that is a good conductor. If you apply an electric field, then these electrons which are in the conduction band, they can take up those small energies and go to quantum states which are available. Alright. In insulators, what happens in insulators? The conduction band is completely empty, this conduction band is completely empty, and the energy gap between the valence band and conduction band is large. This energy gap, we write it Eg, is large. Large means what? Say 3 eV, 4 eV, 6 eV, like that. Now, at normal temperatures like room temperature or so, no electrons populate the quantum states in conduction band. So, this is the structure and at low temperatures this valence band is completely filled, the conduction band is completely empty. As the temperature is increased, thermal energy of the order of kT is now available, but then the gap is so large that these valence electrons cannot cross over that, and therefore even at normal temperatures, room temperature or slightly above also, it is completely empty and no conduction takes place. That is why they are insulators. Okay. In semiconductors, the valence band is completely filled, the conduction band is completely empty, just like insulators. The only difference is this gap. This gap is low, say less than 3 eV or so, typically thumb rule. For silicon it is 1.12 eV. So, although it is still very high as compared to that K into capital T, which is some 0.026 electron volts at room temperature 300 Kelvin, but still it is not that high. So, some of the electrons at say room temperature, some of these electrons in valence band get sufficient energy from thermal interactions and they cross over the gap and occupy quantum states in the conduction band. So, some of these electrons in the valence band, they jump over and they occupy quantum states in the conduction band, and if that happens in the valence band, one quantum state is made available, it becomes empty. So, other electrons in the valence band can go over there, fill that gap and create a new vacant state somewhere else. So, that is how we have this so called holes or vacant states. So, these are the things that we discussed in the previous lecture. So, all this discussion was in terms of rectangles that I drew and called that energy levels and conduction band and valence band, electron going from the valence band to the conduction band on all that. But what is the actual physical picture? Where is the electron? It is not in my diagram. Where is the electron? So, let us connect this energy level diagram to the actual silicon crystal or semiconductor crystal and see how the two things are related to each other. So, if I talk in terms of silicon, it is it has diamond crystal structure. So, each silicon is bonded to 4 neighboring silicon atoms through that sp3 hybridized covalent bonding. So, we will show it here in a 2-dimensional diagram, although it is a 3-dimensional thing, it is a tetrahedral kind of structure, but let us say each silicon atom is bonded to 4 different silicon atoms. So, this is all bonds, it contains 2 electrons. One electron being shared by this silicon, another electron is shared by this silicon, and these two make a bond between these two. Similarly, the bonds are here, here, here. So, the 4 outer electrons, those sp3 electrons, they are consumed in making these bonds. Similar thing happens with this, this whole crystal is there. Now, what is a conduction electron? And what happens when I say that an electron has gone from the valence band to conduction band? What is the meaning in this diagram? All these electrons which are shown here in these bonds, people also show it like 2 lines like this, because 2 electrons are involved in the bond. So, this is also one way of showing. And you also know this is also like methane, you just draw one line and say that it is a bond, covalent bond. So, all these electrons which are there, 2 electrons here, 2 electrons here, 2 electrons here, 2 electrons here and so on, all these are in valence band. If I draw this diagram here, I call this as valence band and this as conduction band. All these electrons correspond to electrons somewhere here in this valence band, everywhere, all the bonded electrons are represented as electrons in the valence band. Now, suppose because of those thermal energies and interactions, some electron gets extra energy. One of these two electrons, let us say it gets extra energy, and then this bond is broken. Suppose this bond is broken. All right. So, this bond is broken and the two electrons are there, one electron is still there and other electron is broken. So, let us take this diagram. So, suppose this is broken. So, there is no electron out here, so just only one electron. Where has that electron gone after getting the energy? It has gone somewhere. This is a silicon ion and that electron has gone somewhere. It is not forming, it is not part of this covalent bond here, and therefore, it can move in the crystal, it can move somewhere else. You have another silicon atoms, other silicon atoms, they are all bonded, like that, and this can go anywhere, here. I will say that after receiving that extra energy, the bond is broken and this electron has gone to the conduction band. This electron is now here in this conduction band. It has occupied a quantum state which is available at these energies, which is much more than this. So, through that thermal interaction, it received the energy, it goes from here to here. That means it goes from here to here, or here means it is going anywhere, and this bond is broken. Now, if bond is broken, there is a quantum state available at this energy which any electron can occupy. So, we say that in this valence band a hole is created. A vacant quantum state is created, and this vacant quantum state can be occupied by any electron. This electron may come from the available conduction band electrons also. So, maybe in the whole crystal you have an electron, free electron here, conduction electron here, maybe a conduction electron here, maybe a conduction electron here, and so on. So, this conduction electron can also come and fill this quantum state. In our diagram, what we will say, there was an electron here and this electron went and filled this hole. So, whole electron pairs can be created by the thermal energies and whole electron pairs can be destroyed because of these thermal energies. Somewhere it is gaining energy, somewhere it is losing energy, and this. So, you have this creation of whole electron pair, and you also have destruction or recombination going on, and given a particular temperature, there will be some equilibrium number, how many quantum states in the conduction band are filled and how many quantum states here are empty. So, that number of electron hole pair, that will stabilize somewhere. Although both ways the process is going on, new whole electron pair are being created and they are recombining, but on the average finally you have a particular number of whole electron pair for a particular temperature. For room temperature, I will give you some data. At room temperature, which is around say 300 Kelvin, silicon has 5 into 10 to the power 22 atoms per centimeter cube. This is the density, number density, how many atoms per centimeter cube. And then the electron hole pair at this temperature, that number is 1.5 into 10 to the power 10 per centimeter cube. So, you can see the fraction per centimeter cube, these many atoms are there, these many atoms are there. And how many are broken bonds? About 10 to the power 10. So, that is the kind of ratio you expect at room temperature. It is a factor of 10 to the power say 12 or so, and that is understandable. Your K into T Boltzmann constant times the temperature at room temperature is 0.026 eV, and that band gap is 1.12 eV, still much larger. So, the probability is small, but even this small probability is very large, because it has created these many charge carriers. All these electrons are now available for conduction, all these holes are now available for conduction. So, these many pairs, these many conduction charge carriers for conduction are made available, even if the probability is very small. And if you want to compare with a normal conductor, say copper, the copper atomic density is 8.4 into 10 power 22 atoms per centimeter cube. Okay. And each copper atom, remember, each copper atom will contribute electrons in the conduction band. So, that number will be of this order. So, the conductivity of copper is much larger than the conductivity of silicon, but nevertheless, if you look for compare with insulator, it is quite large. So, that is how the silicon or any semiconductor will give rise to conduction. Now, these semiconductors, pure semiconductors, are called intrinsic semiconductors. These are called intrinsic semiconductor. By the way, in the previous lecture I showed you an experiment, and I showed that if a semiconducting material is heated, temperature is increased, the conductivity increases, opposite to what happens with the normal metallic conductors, right. And now you can understand why it is so. If you increase the temperature, then this kT will increase, band gap remains the same, that energy gap remains the same. So, if kT increases, thermal energies increases, then there is a more probability, larger probability of electrons going from valence band to conduction band, or those bonds being broken and electrons made free for conduction. So, that probability will increase, that number will increase, the charge carriers will increase, and that is why the conductivity of a semiconductor increases as you increase the temperature. In metals that will not happen. In metals the valence bands are all full, and conduction band will have a fixed number of like copper. Conduction electrons will be fixed. If you increase the temperature, this number is not going to increase. So, there another mechanism where if you increase the temperature, then those scattering from different sites, ionic sites will increase, drift velocity will decrease, and the conductivity will decrease. That phenomena is also there in the semiconductors, but then the number of charge carriers increases so much that that scattering, those things are all becomes less important, and the conductivity increases. Okay. So, we have this intrinsic semiconductor, that means all the semiconducting properties is not because of any outside controls, it is its own, a pure material. And in that case, number of electrons, which electrons? Conduction electrons, and number of holes, that will be equal. You can call it Ni, I for intrinsic. In the previous lecture, I also told that semiconductors are so important, so powerful, because we have the control to tune the conductivity. Why one should use a low conductivity material in any kind of transmission electric currents? Because we have controls, we can change the conductivity according to our requirement, which we cannot do with the copper wires or copper structures. How? That is by putting some foreign some impurity atoms. We are calling it impurity, although we like that impurity. Most of the time people say that impurity is something which has to be avoided, one should be pure and all that. But here we put some impurity atoms in this structure, and that is called extrinsic semiconductor or doped semiconductor. What is this doping and what is this doped semiconductor? You have that structure, that crystal structure, all bonded atoms, covalent bonding everywhere, and this is all silicon. Now silicon, remember, it is Z is equal to 14, and the last one is S2P2. Of course, it is all hybridized in covalent bonding. Now, if you take an element from the next column of the periodic table, where it is the last one is S2P3, like phosphorus for example, or arsenic. You have S2P3, 5 outer electrons. So, if I have a silicon and then using some whatever process, I diffuse some amount of this phosphorus or arsenic into this silicon crystal. And if my process is good, nicely formulated and well implemented, then these phosphorus atoms will go and sit at the site of silicons. Some of the silicons will be replaced by this phosphorus or arsenic. So, what happens if, say, all this is silicon and this particular thing is, let us say, phosphorus. So, all this is silicon, all this is silicon, all this is silicon. But here I am bringing that pentavalent material, that a particular atom is sitting here. It is a neutral atom, it has as many protons as the number of electrons, and then this neutral atom comes here. There are 5 outer electrons. Those 5 electrons, where will they go? In this particular crystal structure, that the silicon has, 4 of these electrons will be part of this bonding. 4 of these electrons will be part of this bonding. Where is the 5th one? The 5th one will not be at this energy level. It will be at a higher energy level. So, it is bonded to this, but then the energies are much higher. Is going on a say, larger orbit or so, and then the bonding is very weak. Bonding of this particular electron to this is quite weak. Calculations can be made, and this bonding turns out to be, say, few tens of MeVs, say 50 MeV, right. So, like that. So, this particular extra fifth electron, for this the energy which is there, it is much larger than this valence bond energy. So, if I again go to my valence energy diagram, we have this valence band here, we have this conduction band here. All these bonding electrons, they have energies which are lying here in this energy band, in this width, in this range, but this one has a very high energy. How high? It is close to this conduction band, somewhere here. So, these new energy levels are created, new energy levels here just below this conduction band, and this gap is small, it is in milli electron volts, say 50 MeV. This gap is small. So, that means you give 50 MeV and this electron will be detached from this parent atom. So, if that happens, what will happen? This will go to the conduction band. So, the electron is already here in these quantum states. These electrons like this, of course, you do not put one phosphorus atom, even if it is ppm, 1 part per million. So, per 10 to the power 6 there is 1, and then remember per centimeter cube you have 10 to the power 22. So, there are many such. So, all these electrons which are there, they are in these levels, these are impurity levels or donor levels. So, they are created here, but then 50 MeV is a small energy. So, from thermal interactions easily this gap can be crossed and all these electrons will move, most of them will move into the conduction band. Moves into the conduction band means it becomes free to move anywhere in this crystal, going from this atom to that atom to that atom, and so on. So, that is how you will get this. So, now what happens? From the usual electron hole production and recombination, you had some number of holes here and some number of electrons here, which was Ne and NH. On top of that, all these electrons are now made available. So, in the conduction band, now you have many more electrons than this number of holes here. For each hole you do have an electron there, but these impurity levels, they are giving us many more electrons in the conduction band. So, Ne, number of conduction electrons, is much larger than number of holes because of this impurities. And there is yet another phenomena. This number of electron hole pairs that I was talking, that depends on the temperature, that is an equilibrium state. New holes electrons are being produced and they are, the electron hole pairs are destroyed because of recombinations, and some equilibrium thing is happening. The probability of this creation and probability of this recombination, they become same at certain level. Now, if there are too many electrons here, the probability of electron going into this hole, recombining this hole, becomes very large. Okay. In intrinsic case, you had much fewer number of conduction electrons. So, an electron going and filling that vacancy, that probability was less. If you think in terms of the crystal, in the actual crystal, yes, if there is a bond broken here and there are some free electrons available, those free electrons can come here and fill this gap. If there are many free electrons available around, then the probability of someone coming here and filling that gap will definitely increase. So, the recombination rate of filling these vacancies will increase, and therefore, the number of holes will further go down. In the intrinsic case, we had these number of holes, some number of holes, but when we are putting impurities, pentavalent impurities, we are increasing the number of electrons, fine. At the same time, the number of holes is decreasing because of this recombination, increased rate of recombination. And so, if I say that if I compare with this intrinsic one, let us put some symbol here. So, if I compare with this, in this case Ne is larger than Ni, that is understandable, and also this NH, this is Ni, no need of that dash, Ni is there, and this NH is, but NH is smaller than Ni, that is important, that is interesting. Not only that the number of electrons has increased, the number of holes has decreased because of the increased recombination. And then one can do some mathematics, some theory, and it turns out that this Ne into NH, that turns out to be N square, very interesting, Ni square, very interesting. Ne is increasing, NH is decreasing, but the product remains same. So, if there is no doping, that product is Ni into Ni, and if there is doping, still the product remains the same. So, that is very interesting. Okay, one can do some numerical on that. Okay, so numerical problem. Suppose you have a pure silicon, no doping, and at room temperature, the total number of atoms per unit volume is per unit volume is 5 into 10 power 28 per meter cube. Per meter cube. Previously, I had talked in terms of per centimeter cube, and that is why it has gone to 10 power 28 and not 10 power 22. And then at this temperature, let us say the hole density and the electron density, they are equal intrinsic density, and that is, let us say, 1.5 into 10 power 16 per meter cube. Now, we put a pentavalent impurity, arsenic, let us say, arsenic, and 1 ppm. What is ppm? ppm means parts per million. That means 1 in 10 to the power 6. So, whatever is the number of atoms per unit volume, 1 part in 10 to the power 6 is replaced by this arsenic. Now, the problem is to find after this doping how much is this electron density, conduction electron density, Ne, and how much is the hole density, NH. So, that is the problem. I have copied this data on the board, and let us solve it there. So, how do I solve this problem? The number of extra electrons, conduction electrons that we have created through those impurity levels, that will be 1 per impurity atom. Okay? 1 atom pentavalent, 5 electrons, 4 go in bonding, 1 is extra, that goes to the impurity level, and from there it goes to the conduction level. So, that Ne, number of these electrons which are created due to this doping, that will be 1 ppm. That means if you have 5 into 10 to the power 28 atoms, 1 by 10 to the power 6 of that is 5 into 10 to the power 22. These many new conduction electrons are being injected. Then there are conduction electrons from the intrinsic processes, but that number is small. That number is 10 to the power 16, very small as compared to this is very small. So, the actual number is this plus this, but is so small that you can take that Ne is just equal to this. And then Ne into NH, number of electrons into number of holes, that should remain the same, that is independent of doping. So, this is your Ni square, and Ni square you can take it from here, it is 2.25 and into 10 to the power 32. Of course, the unit will be also squared and all that, but anyway that is I am talking of now in these units. So, what is NH? NH number of holes will be equal to this 2.25 into 10 to the power 32 and divided by Ne, and Ne is 5 into 10 power 22. So, work out how much is this? How much is this? This is 0.45 into 10 to the power 10 or 4.5 into 10 to the power 9 per meter cube. Okay, so the number of holes has decreased. Originally this was the number of holes, it has decreased from there. Now, in these type of extrinsic semiconductors, the number of electrons, conduction electrons is much larger than the number of holes, and therefore, they are called N type semiconductors. So, these when you dope these things and Ne becomes much larger than NH, then you call it N type semiconductors. You have the other variety where you do not go into that pentavalent things, you go for trivalent things like boron or aluminum or gallium. They have 3 electrons in the outer shell, S2p. So, if I make a semiconductor, take a silicon and then do all that thermal processing, diffuser, all whatever is prescribed, and diffuse some of these trivalent impurities in that, what will happen? So, once again if I go for the structure, I have silicon here, I have silicon here, everywhere I have silicon, and they are all bonded to the neighbors, and somewhere here we have a trivalent, let us say boron. So, this is all silicon. It is important that during this doping process we do not destroy the crystal structure, that crystal structure should remain the same, so that you still have all those covalent bonding and on those things. So, you have all these things here, all the bondings are there, 2 electrons per covalent bond. But here boron comes with 3 electrons only. So, it can participate in 3 covalent bonds, the 4th covalent bond it cannot participate, and therefore, this particular one of the states will be empty. So, you have 2 electrons here, 2 quantum states, but because this it does not have 4 electrons, it only has 3 electrons, it has come with 3 electrons, and therefore, you have a hole here, you have a vacant state here, this bond is broken. So, a hole is created, but this hole, the energy of this hole is different. If there is a hole created here, if there is a hole created here, silicon bond, if that is broken and the hole created here, that is different energies. If an electron comes and sits here, makes a bond, electron comes and sits here, makes a bond. These energies are different because the nucleus is different, this nucleus is different, this nucleus is different. So, new quantum states are available, in this energy range somewhere near that, but not exactly in the original valence band. These new energies are slightly above the valence band. So, if I have a diagram, if this is your valence band, if this is the conduction band, you have all these quantum states here at these energies, you have all quantum states available, and these correspond to the usual covalent bonds between silicon. But a bond between boron and silicon, that will have energy which will be slightly higher than this, and it will be somewhere here. So, the quantum states are created, new energy levels are created. Let me use some other color. So, these quantum states are created. These are now impurity level. Or acceptor level. Why acceptor? This quantum state has a larger energy than this quantum state. Okay. This quantum state has an energy which is shown here, slightly above the valence band, whereas this these quantum states are having energies which is here in this valence band, slightly higher. If an electron wants to break from here and fill this vacant state, the energy is slightly more, some energy is required. How much? Once again that small energy is few tens of milli electron volts, say 50 MeV or so, and that can easily come from thermal interactions. So, in that case any of these things can break from here, get some thermal energy and fill this state. And so, the electrons can come from these levels. What are these levels? Here are those levels, silicon. So, from here it can come to here, that means somewhere here it can break and it can occupy this quantum state. So, we say that electrons can go to these states and holes can be created here. So, as many atoms you are doping, each atom is creating a quantum state in this impurity level, and since this is small, very easily electrons from this valence band are going and sitting here, and therefore, the holes are created in valence band. Okay. So, in this case the number of holes will be larger than number of electrons. When I say electrons, remember it is conduction electrons, and holes are in that valence band. The same story once again, if you have too many holes and few electrons coming from that intrinsic processes, so and their corresponding holes are there, but then those holes are much smaller in number. So, the number is dominated by the impurities. So, if there are too many holes and you have few electrons, then the probability of one electron going and filling some hole will increase. If you have same number of holes, then there is some probability, but too many holes. So, electron can either fill that or fill that or fill that or fill that, the probability will increase manyfold. what will happen? That creation remains the same, the destruction becomes larger, and therefore, this number will reduce further. So, the same story, the holes number will increase, the electron number will decrease, and that product NeNH will remain at that Ni square. Now, since here the holes are in a larger number than electrons, we call them P type semiconductors. So, these are called P type semiconductors. And now you know where is that control of conductivity. That control is in doping, how much I am doping, and whether I am doping it uniformly across that silicon crystal, or I am creating a gradient, density gradient of that doped material, how I am monitoring that, that will give me the handle to change the conductivity at will. How much conductivity I need, if I need conductivity in this portion, more conductivity, in this portion less conductivity, I can do that. If I need more holes here, less electrons there, I can do that. In the same crystal, in the same wafer, I can diffuse phosphorus from one side, I can diffuse boron from other side with different concentrations, or phosphorus with different concentrations. I can play with it and I can have a great control on conductivity profile, and that is how these things become very, very important. So, now let me talk of conduction by holes and by electrons. So, let us say we have a valence band, and in this valence band we have certain holes, certain quantum states are empty, and then we have a conduction band in which certain quantum states are occupied. It could be N type semiconductor or P type semiconductor. So, there are some conduction electrons available and some these holes are available. And in the crystal, if you think, once again the same diagram like this, covalent bonding everywhere, and some of the bonds are broken, some of the bonds are broken. So, you can also do that, let us say this bro. So, at some places you have holes, at some places you have electrons. In general, if you do not apply any electric field, you do not connect it to battery, nothing. In general, these conduction electrons, which are free to move, almost free to move in this crystal, they will be going from here to there to there randomly, sometimes combining with the hole, sometimes moving at some other site and so on. Similarly, when the electrons go somewhere and fill that hole, if valence electrons can also do that. Valence electrons can break a bond here and go, some hole is created here, then this bond can be broken, this electron can go here, sometimes from this side, sometimes from that side. You can picture it as the electrons are moving in random directions and the holes are also moving in random directions. The conduction electrons, they go from one atom to other atom, and then when the valence electrons, they also change sites. If there is some hole here, some empty quantum state here, the electron, neighboring electron can come and fill that. So, the hole has moved from one side to the other side. Holes are also moving randomly in this crystal, and then you connect it to a battery and you apply an electric field in this material in certain directions. So, you apply an electric field in certain direction. So, this electric field will exert forces on all the electrons, and if it is possible for the electrons to take up that energy and go somewhere else, they will respond, otherwise they will not. So, if the electrons are there and this electric field is there, the movement of electron will be according to that electric field, opposite to the direction of electric field. So, on top of that random motion, systematic drift velocity will be induced. What happens to the holes? The valence electrons will also feel the pinch of this electric field. But in the neighborhood, if there are no vacant states, they will just stay there, they will not respond to the electric field. But if in the vicinity there is some broken bond and the electric field is there to push the electron in proper direction, in that direction of the hole, remember the force is opposite because of negative charge. So, if the electric field is there to push the electron in a certain direction, and in that direction only in the neighborhood some broken bond is there, this valence electron will be prompted to go there and fill that. So, because of the electric field, the holes will also move in the preferred directions, and the electrons will also, conduction electrons will also move in the proper preferred directions because of this field, and therefore, you have a conduction, you have a current because of the electrons and also because of the holes. So, the total current in that material will be because of these conduction electrons and because of these holes. Of course, the two are not equal. You do not think that number one, the number of electrons can be very large as compared to number of holes, or number of holes can be very large as compared to number of conduction electrons, and therefore, these two need not be equal. And not only that, the mobility, if an electric field is applied, how much current it will generate. So, that is also different for electrons and for holes, and therefore, the two need not be equal in any case, even for intrinsic semiconductors. Nevertheless, you have conduction because of the holes, that means you have conduction because of the bonded electrons. It is a new feature. In metals that does not happen. If you have free electrons, if you have conduction electrons, fine. The metals, in metals you have those, and therefore conduction. In semiconductors, you have conduction because of these conduction electrons and also because of the valence electrons, which are bonded. They are only changing atoms from this bond to the neighboring broken bond and so on. So, both of these contribute to the conduction in semiconductors. So, let me summarize what we did in this lecture. Essentially, we tried to connect the diagrams that I make, conduction band and valence band. These diagrams we make, and what do these diagrams mean in terms of the actual crystal? That was the first part. And we said that in semiconductors you have atoms, and these atoms are bonded. The outer electrons of the atoms take part in this covalent bonding, and then all these electrons which are used in these bondings, these electrons will have energies which will be in this valence band. So, these quantum states here correspond to the bonding electrons, whereas if some bond is broken and the electron goes somewhere else in the crystal, which is weakly bound to some atom, that electron will have energy which will be in the conduction band. Then we talked of how electrons jump from valence band to the conduction band. So, if you have a electron which is sitting here in this valence band, and then we say that it goes to the conduction band, what do we mean by that? So, the meaning of that is some bond is broken, some bond, two electrons are here in this bond. So, this is broken and one electron gets freed from this bond, and then it can go somewhere else, weakly bound, can change atom from one atom to other atom, and therefore, can move in the entire crystal. And then we say that the electron has gone from this bonding to this free state, not free state, but nearly free state, and here we say that a hole is created. When this electron goes from here to here, we say that a hole is created. This particular quantum state which contained electron is now vacant. Okay. Then we talked about intrinsic semiconductor. When you have not doped anything, that is known as intrinsic semiconductor, and in that case Ne and NH. What is this? This is number density of conduction electron, and this is number density of those vacant states or holes, all per centimeter cube or per meter cube, whatever you take, and then you have Ne equal to NH, which we write Ni. Now, the most important part, you can do doping, most important part, because this is the doping which gives us control on conductivity. So, you can dope certain elements which can create more holes than electrons, or which can create more electrons than holes. So, if you dope pentavalent impurities like arsenic or phosphorus in silicon, then you get what we call Ne is much greater than NH. Okay. Then we there is very important part to understand about this doping, that you do not have charge density, right. When you put this pentavalent impurity and you have many more electrons than holes, do not think that the material gets negatively charged. These type of semiconductors are called N-type semiconductor. And why N-type? N-type because of this N stands for negative. And what is negative? The charge carrier, the majority charge carrier, that is negative. That is negative. These are electrons, and that is why it is called N-type semiconductor. But the charge density is still 0. You have charge carriers, but not charge densities, because you only dope neutral atoms. You only dope neutral atoms. What happens if I apply an electric field? If I have this semiconductor, electrons are there, holes are there, right. One may be larger, one may be smaller, or they may be equal. If I connect it to a battery, if I apply an electric field, what happens? This electric field, as usual, tries to drive electrons in one direction and holes in another direction. So, because of both you have current. So, the current is because of the electron movement and because of the hole movement. So, this is what we did in this lecture, and from here we will take about devices, the p-n junctions and other things in the next lecture.